All right, so today's lesson is on speed and velocity. So yesterday we did position and displacement. Today we're going to be doing speed and velocity. So first, let's go over the differences. Let's say we have this example. We have a track, a circular track, and we're going to have a runner start here, go around the circular track, and finish there. And let's say we want to figure out how far they went. Well, remember, we can look at either distance or displacement. Now, distance is a scalar quantity, so it doesn't care about direction. So if we run from here around to here, our distance we traveled in this example, 200 meters. But displacement is a vector, so it cares. Displacement is just your change in position. So comparing our final position and our initial position, if we were to draw that as a vector, it looks like this. Even though that's not where we ran, we took a different path. But if you just compare where we started and finished, that's our displacement, which would be like this. If you just continue this example and you ran all the way back to your starting position, then your displacement would be 0. I mean, yeah, you may have run about 200 meters, but technically you haven't moved from where you were before. You're in the same position. So even though it would have taken energy to do that, you haven't gone anywhere. All right, so what about speed and velocity? Well, same thing. Speed is a scalar quantity. And so notice we don't have a vector arrow above our variable. We still give it the symbol v though, just without your vector symbol. And similarly, we don't put a vector symbol above this d, because this would be distance, which is also a scalar quantity. So in our example, if we wanted to calculate speed, which is a scalar, we would simply do distance over time. Now let's say this took 10 seconds. So you would simply write 200 meters divided by 10 seconds, and you would get a speed of 20 meters per second. But what about displacement? Displacement wasn't 200 meters, it was 82.5 meters. And velocity, if we wanted to calculate velocity, velocity is a vector. That's the difference between speed and velocity. If I said you were on a highway moving at 100 kilometers per hour, I just told you your speed. If I said you're moving 100 kilometers per hour south, I just told you your velocity. So this is our velocity, and it's a vector quantity. And if we want to calculate it, we're going to use displacement. So in the example we just looked at, right, our displacement was 82.5 meters. And our time, well, same amount of time. I forgot the 2 here. 82.5 meters divided by 10 seconds. And we only get 8.25 meters per second. So our speed and velocity are very different. Now this is both average speed and average velocity because it's taken over a time interval. That's why the T symbol has a delta. Because remember, delta means change. It's over a certain interval. In this case, between a recorded time 2 and a recorded time 1. However, there is something called instantaneous velocity, and that is your velocity at any moment in time. The best example would be a speedometer in a car. So if you're driving a car and you look at your speedometer, that tells you your velocity now. Well, actually, it would tell you your speed unless you have a car that actually, some cars do show you the direction you're moving in as well. Other cars don't. So that depends on what kind of car you're driving. Let me just pause. Notice that when we calculated velocity, we got 8.25 meters per second. But since velocity is a vector, we need to put a direction here. Now we don't specifically know the direction, so in our case, we could just put some sort of southwest direction. But I'll go over directions in more detail later in the unit when we actually go into two-dimensional vectors. But for now, let's look at some examples on the next page. And we're going to look at graphs. Now yesterday I introduced a position time graph. A position time graph shows, well, your position over a certain time interval. So let's look at this position time graph. We have someone or something, a car, I don't know, but an object which is starting 20 meters east of this origin. And then they're moving at a constant rate, because we have a straight line here, constant rate towards the origin. And then 5 seconds later, they stop. It's just a horizontal line. Their position is not changing. So they've stopped. Maybe just to take a break. And then they continue after another 5 seconds. And again, a straight line, so constant velocity. In this case, if our positive direction is east and they're moving towards the origin, they're actually moving west. Even though their position is east, they're moving west. And then we cross the origin and we're still moving west, but now our position is also west. And then we immediately turn around and start running or driving east at a constant velocity until we get back to the origin. So this is what's happening. But we can change this position time graph into a velocity time graph. And how we do it is the slope on a position time graph is your velocity. Remember, velocity is displacement over time. Right? Let me rewrite that. So velocity is displacement over time. So if we were to just look at this first portion right here, we have a certain change in position from here at 20 meters east to here at 10 meters east. And a change in position represents our displacement. I can rewrite this as final minus initial. And that's all over some time interval. Our time interval in this case went from 0 to 5. And your slope is rise over run, or displacement over time. So our slope on a position time graph tells us our velocity. So in this case, without calculating an exact number just yet, but you can see the slope is a negative slope. So our velocity will be negative, which means if we were to write a velocity time graph, where east is our positive direction, we are actually moving west. So we have a negative velocity. And it's a horizontal line because it's constant. It's not changing. So for that whole first 5 seconds, it's not changing. Now I wrote it at -2 because if you wanted to calculate this, here you have a displacement of 10, or actually -10, and a time of 5. So -10 divided by 5 is -2. Over here at B, we're not moving, and so your velocity should be right here at 0. And then again, similarly, you have a negative slope, negative velocity. For an instant in time, you're not moving. And then once again, now we have a positive slope, so positive velocity. Notice that our velocity time graph is discontinuous. Now in the real world, it wouldn't be that way, because to go from one velocity to another, you would have to accelerate. But we'll talk about acceleration in a different lesson. So for now, it's going to be a discontinuous graph. So our next example, now we have a position time graph that isn't a straight line, it's curving. Now this is more realistic. Right? A curved position time graph does represent acceleration. Because if we look at the slope at any point, it's changing. So if I drew a slope right at that point, it looks like this. If I drew a slope right at this point, it looks like this. So what I'm drawing are tangents. Because the slope is changing, if you want to figure out your velocity at any instant in time, or like I said before, your instantaneous velocity, you have to find the slope of a tangent. So let me just review what a tangent is. A tangent is a line that only touches the curve at one point. So let me draw you an example here. Let's say I had a curve like this, and I'll draw something like this. That is not a tangent. It's terrible. It goes through the curve here and here. However, if I were to draw a line that perfectly touches, so not like this, not like this, but keep going, and it perfectly touches just one point on the line right there, then that is the tangent to that point on the curve. And the slope of that tangent will tell you your velocity, your instantaneous velocity at that point. Now, to figure out exactly how to draw the tangent at that point, you need calculus, which you'll learn next year in grade 12. But in grade 11 physics, we're just going to draw an estimate to what the tangent would be. And if I'm, say, marking a test or something, basically any line that looks like that yellow line is good. But the blue line, which is clearly going through 2 points on the curve, is not very good. All right, so once we have our slope, once we have our tangent, we can calculate the slope. Just choose any 2 points on that tangent, like this one and this one. And we can look at our displacement and our time. So our displacement is change in position, which from here looks to be, let me just go with about 35. So our final position is 35 meters forward, minus our initial position, which was right here. This looks to be about 15. So 15 meters forward, all divided by our time, which looks like final minus initial. So 3 seconds minus 1 second. Right, so we get 35 minus 15, which is 20 meters forward, divided by 2 seconds. And that will give us a velocity of 10 meters per second forward. So let me explain again instantaneous velocity versus average velocity. If we have a position time graph where we just have a straight line, now your average velocity is between any 2 time intervals, let's say t1 and t2, and so you can find the slope like that. But your instantaneous velocity is at any time interval. Now if you have a straight line, right, like here you'd have an instantaneous velocity, here you'd have an instantaneous, here you'd have an instantaneous velocity, here you'd have instantaneous velocity. But for a straight line, since your velocity is constant, in this case your average velocity and your instantaneous velocity are the same. But what if you had a curve? So let's say you're doing this, and you wanted to try and find your average velocity between, let's say, this point t1 and this point t2. Well, your average velocity, you would draw a secant, which would be a line connecting t1 and t2. So that is your average velocity, would be the slope of that secant. But if you wanted to find your instantaneous velocity at one instant in time, let's say I wanted to know exactly how fast I'm going at this point t2, I would draw a tangent to that point like this, and the slope of that tangent tells me my velocity right at this instant. So notice that these slopes for the secant and the tangent are different. But again, if I wanted to find instantaneous velocity at t1, I would draw a tangent line. It's not the best tangent. Try that again. Tangent line, still not the best, but hopefully you get the idea. So this first blue line is our tangent at, let's say t1. And the second blue line is our tangent at t2. And the red line would be our secant between t2 and t1. Right, so this is average velocity. And our blue one, we can call this instantaneous velocity at time 2, and we can call this instantaneous velocity at time 1. And we will now go over our last example. So above we looked at position time graphs and looking what they would look like if we changed them into a velocity time graph. And notice that we found the slope of either the secant or the tangent, and that would tell us our velocity. But what if we started with a velocity time graph like this one? So let's look at what's happening here. Let's say we have a car or a person, actually maybe a person, this would be a very slow car, but we have a velocity in meters per second. So on our axis we always show what it is, what the units are, and what the direction is. So we have meters per second east. So we have some person running at 3 meters per second east. Now it's a horizontal line, so that velocity is not changing. So it's a constant velocity. And then they slow down. It takes about a second for them to slow down. You can see velocity is changing here. So that would be a curved line on a position time graph. And then again, we keep a constant velocity. Now we cannot directly determine position from a velocity time graph, but we can determine displacement. So let's look at this first portion where our constant velocity is at 3 meters per second east for the first 4 seconds. And you can see it's just shaded in here. Now it's shaded in there because what would happen if we found the area under that graph? Well, area of a rectangle is just, well, length times width. So we are actually doing meters per second, okay, multiplied by, this is minutes, but we can convert minutes to seconds. So what would happen if I did meters per second and times it by seconds? Well, the seconds would cancel and you just end up with meters. So by finding the area under a velocity time graph, it'll tell you your displacement. So this tells you your displacement, not your position, your displacement. So if we look at this first example, and if we wanted to figure out the displacement in the first four minutes, what we can do is find this area. So we have 3 meters per second multiplied by the length, which is 4 minutes. But we want to change that into seconds, and since there's 60 seconds per minute, we'll multiply that by 60 seconds per minute. And so minutes cancel here, seconds cancel here, and we'll get an answer, which is in meters. So 3 times 4 times 60, and we get 720 meters. And since our answer is positive, and our positive direction is east, we know our displacement was east. Now it's the same with B. I wrote in B for you here. There's 2 ways to do that. If you remember your equation for the area under a trapezoid, you can use that. Right? Or you can actually split it into a triangle and a rectangle and find the area of both and add them. But for now, if we were to look at C, okay, C is, we go from 5 seconds to 10 seconds at a speed of 1 meter per second. So length times width, we get 1 meters per second, times by, from 5 to 10 is minutes, not seconds. And we need to convert that into seconds, so multiply by 60 seconds per minute. And we should get 300 meters. So to figure out your total displacement, you would just add all your previous displacements. So 720 plus 120 plus 300, and we get a total displacement of 1,140 meters, all positive east. Now, if you had an example where maybe this went into the negative and did this, well then for this portion you would find the area still under the graph, but notice you would have a negative velocity. So it would give you a negative displacement. But that's just telling you your direction. If you get a negative displacement east, negative east is the same as positive west. And so it's just telling you that your displacement is west if your velocity is negative.